Alright, this 4.5 section is on isosceles and right triangles. We're going to look at a little bit of both. First thing we want to do is grab your protractor as a straight edge and just draw a line. Yeah, I gave you some space on that little place on your notes. Just draw a line. We're going to actually construct an isosceles triangle. So we're going to show you how it works with a compass, how you can take a compass and make an isosceles triangle. So take your compass and put it on one side of the line you just drew. Now, you just have to make sure you're past halfway to make an isosceles triangle. I'm going to actually go farther, and I'm not going to be exactly, but just make it a little bigger so it's a little bigger isosceles triangle. And then just make an arc. And make that same arc from the other side. Don't change your compass at all. So make the same arc from both sides of your segment that you drew. And then take your straight edge, and where the intersection of those two arcs was, connect that to each endpoint. So just take your ruler and connect it, or your protractor. Connect it to each endpoint. And then to verify that it's isosceles, do you remember what the definition for isosceles was? Two equal sides, which we should have done by making the two equal sides with our compass. So to verify it, take your protractor, the ruler part of it, or if you didn't get a ruler part of it, then use a ruler, and actually measure the two sides and see how they came out. For me, I got an 8 centimeter side, which looks like exactly 8 centimeters. And then on the other one, I have, you can see mine's perfect, another 8 centimeters. So then on the sides, I'm just going to put 8 centimeters. You're going to put whatever your length was on both sides, just to show that it is indeed an isosceles triangle. Now, let's label our triangle with an A, B, and a C. So we'll put A, B, C on here just to have some letters. And to show congruency, we could just put these little slashes or tick marks. That allows us to say that these two sides are congruent to each other. That's what those little tick marks show us. And you could also put the arcs in there as well. So you could put arcs in there. Arcs also show congruency. Whoops. So you could put an arc. This angle right here is congruent to this angle over here. So you could show that the two angles are equal by actually measuring them. So get your protractors out and let's actually measure the distance, and let's see if that's actually a true statement that the two angles are equal. So I'm going to put my protractor on my base, so my base is 0, and it's going to go up to 58 degrees. So for me, my first angle is 58. If this is truly isosceles, then this should also be 58 degrees. And if you look at it, it is 58. It goes right through the 58 degree line for me. Your angles will be completely different. So mine are 58 degrees. So hopefully you can see that whenever you have an isosceles triangle, you've got two equal sides and two equal angles. So we took our ruler, we measured the sides, we took our protractor, we measured the angles, and we've got what we have an isosceles triangle, and we basically just proved our isosceles triangle theorem. The theorem says if two sides of a triangle are congruent, then the two angles have to also be congruent. So that would be basically proving the isosceles triangle does work. And I'm hoping that you guys measured your angles and got the same two angles on your paper to show that it works for all triangles. No matter what shape of an isosceles triangle you drew, if your two sides were equal, your two base angles were also equal, your two bottom angles. Now I do want you to also label the correct sides of our isosceles triangle. This side down here is a base. And these two in an isosceles triangle are called legs, just like the right triangle. The right triangle, the two sides are legs, and then we have a hypotenuse. In an isosceles triangle, we also have two legs and a base, not a hypotenuse because it's not a right triangle. Across from the base, if you look straight across from the base, you're going to get what we call a vertex angle. It's called a vertex angle. And that's the top angle. Straight across from the base, we call it a vertex angle. So those are just the pieces of the isosceles. Now, Bianca, if you want to sit here during notes, you can. That way you can see better. I know it's a little challenging with that stuff going on. So. Now, since we know that the base angles are congruent, which we just learned in this theorem right here, and we saw in our drawing that the base angles are equal, could we figure out this top angle without measuring it with our protractor? Because what do we know about all three angles in a triangle? They equal 180. So I could simply take a calculator and add the two 58s together. 58 times 2 if I wanted to. And I get 116. I could take 180 and subtract 116 from 180. And my top angle is going to be a 64-degree angle. So then I could take my, I could just put 64 degrees. Now you could do the same for yours because you had a different angle as I did. So you could add your two angles together, subtract it from 180, and you'll get your top angle. What if, though, in example 1 here, they didn't give you the bottom angles, they gave you the top angle. Now this is not 352. There is a decimal point there, 35.2. It doesn't show up very good, but it is there. I don't know if that would be better to leave it like that. But it's actually 35.2 degrees. So what would be the process of figuring out the two bottom angles? Daniel?
180 minus 35.2.
Okay, so that amount would give us what the two angles have to add up to, right? And what do we know about them? They're equal, so what do we do? Divided by 2. So just what he said is we would take 180, subtract the 35.2 angle to find out what the other two have to add up to. Cut that in half because each one is the same. So 144.8 is what these two have to add up to, divided by 2 since they're both the same, and you get 72.4. So that's on SchoolNet tonight. So if you go on your SchoolNet, there's a couple of problems like that where you have to find the measure of an angle. Okay, so each base angle there is 72.4 degrees. How are we doing? Can we move? All right. Moving on. Again, the video will be online, so if you miss any part of it, you can get it there. Okay, we've got a cable corporation has installed an antenna perpendicular to the ground. That's information that we need. Here's the antenna, and it's 90-degree angle to the ground, perpendicular. Okay, the antenna was held steady by guy wires of equal lengths. So this wire coming from the top to the ground is the same length as this guy wire from the top to the ground. Are the guy wires anchored or anchors on the ground the same distance from the antenna? Are these amounts AC and CB the same amounts? Is the anchor the same distance away from the antenna? Here's what we call a flow proof. First, we look for given information. Remember where they said the antenna was held steady with guy wires of equal lengths? So that means the two guy wires, P8 and PE, are equal lengths. That's given to us. That's given to us in the problem. The guy wires are equal. You might even want to underline equal lengths to show that those are equal. That's how we got the given. And you might want to put tick mark, or it's probably already on your picture. It already has the tick marks. Now, it also says that it's perpendicular to the ground. PC is perpendicular to AB, and that's another given statement to us. That was given to us in the problem. Now, working from this information, we would just look at the picture and we would try to find things we know to be true. We can only use true statements in a proof. Do we know that PC congruent to PC is a true statement? Because of what? Reflexive. It's like looking at a reflection when the same thing is congruent to itself, and that's a common segment in both triangles. That's called reflexive property. Do we know that when we have perpendicular lines, we make two angles that are 90 degrees, and they're both congruent because they're both 90? Okay, so that would just be definition of what perpendicular lines do. They make two 90-degree angles. So that's got to be another reason for us, because it's also something on the picture that we know. We know if they're 90, we know if they're perpendicular, they're both 90 degrees. Now, thinking back to this last theorem that we just did, the isosceles triangle theorem, where it says if two sides are congruent, then the two angles have to be congruent. Does that apply here? Do I have two sides of this triangle congruent? So what does that tell me about angle A and B? They're congruent, and it's just the theorem we just learned, the isosceles triangle theorem. That was the theorem we just learned, is that those two angles must be the same because they're base angles. And whenever you have two sides congruent, the two angles must also be congruent. So is there now enough information to show that these two triangles are congruent to each other? Well, I think a tick mark means a side, right? And then I have another side, two sides congruent. I also have the angles that we said were here. We had the right angles, right? And then we have the middle sides in common, right? So really I have an angle side side. That's a bad word if I just did the letters. So that doesn't work. But I also have angle A and B, right? So now what do I have? I have angle, and another side. I have AAS. So that's the AAS theorem, because now I have angle, side, and my other side was over here. So I don't have SAS at all, because the angle would have to be up here, or I'd have to have a side down here, which I don't. That's what we're trying to prove. We're trying to prove the two bottom sides are congruent. Once you show that the triangles are congruent to each other, once you've said that this triangle equals this triangle, now you can say that all corresponding parts of congruent triangles have to now be congruent. So CPCTC. Once you've got the two triangles the same, now all pieces have to be the same. So now you can say that those two are definitely congruent. So that did prove that the guy wire anchors are the same distance away from the antenna. That did prove it because we had the two triangles were the same. All right, moving on. So 3 letters, or 5 letters, C, P, C, T, C. Let's talk about a perpendicular bisector. You've seen both of those words, right? Perpendicular means makes right angles, 90 degrees. Bisector means cutting in half. You're bisecting something, you're cutting in half. Let's draw a perpendicular bisector down here. You have some room at the very bottom. Make a line, a straight line about halfway between the bottom of the paper and the where it says construct a perpendicular bisector. And we're going to cut this segment exactly in half, and we're going to make it a perpendicular line when we do it. And we actually did this once before with our constructions, and I called it a special name. I called it the fish. I don't know if you remember that, but we've done a construction called the fish. Here's what it looks like. You put your compass at one end point, and you open it up so it's more than halfway. And then you make an arc all the way, like half of a circle almost. And then you put your compass on the other end point, and you make the exact same arc from the other end point, and they will overlap. If you went past halfway, the two arcs will overlap, and that kind of looks like a fish. So we call it the fish. Then you take your ruler and you draw a straight line connecting the two intersections. So you draw a straight line that connects those two intersections, and you've made your perpendicular bisector. Basically what it does is it bisects the segment. So what I could do is I could put my tick marks here and here to show that it's cut. This point right here is the middle point. It made two equal pieces. And you could also put in your little boxes for right angles down here. But these are both right angles. So that's a perpendicular bisector. Now I want you to take your ruler and draw 6 lines, and I'll show you where they are. I want one line that connects this where you intersected to each endpoint. That's one line there, and then the other line to the other endpoint. That's 2. Okay, watch mine first so you can see them. And then I want you to pick any point inside here, anywhere you want, and I also want you to connect that to both endpoints. And then any point on the bottom, I don't care where you pick it underneath, you're going to draw 2 lines there as well. So I'll give you a second to draw those in, and then I'm going to have you do some stuff with it. I'm going to put A and B on the 2 endpoints, just so we have letters on there. And I'm going to put letter C as the intersection between the 2 lines. So you've got A, B would be the 2 endpoints. You've got C as your intersection. And I want you next to take your ruler or your protractor with a ruler on it and measure the length of the 2 farthest ones. So these 2 ones that were on the outside here. For me, that's a 5.5. And then I'm going to measure this side. And I get another 5.5. So for me, these outside ones were both 5.5 centimeters. So what I could do then is I could put a tick mark here, or 2 tick marks, because I already used up 1. So I could put 2 tick marks here to show congruency. That shows me that the 2 farthest sides out here are congruent to each other. So basically, think about it here. If I drew this big triangle, what kind of a triangle did I draw? This big triangle that I'm highlighting right here. That's isosceles because it's got 5.5 sides. So I drew basically an isosceles triangle. Now, what do you think happens if you measure these two pieces? They're also equal. I could put 3 tick marks here and 3 tick marks here. What would you think will happen if I measure the bottom 2 lines? They're equal. They'll make an upside down isosceles triangle. They're going to be equal as well. So any point, I could choose any point that I want to, and it would be the same distance from A as it is to B. Same distance means equal distance or means equidistant. So here's your theorem for the perpendicular bisectors, and we just proved it by drawing all these lines and measuring these lines and making sure they're the same distance. But the perpendicular bisector theorem says any point on the perpendicular bisector is equidistant to the 2 endpoints of the segment. So I could take my ruler again, and I could measure these bottom 2. That's going to be a 5.2 on that side. And I could measure the same thing here. And it would be a 5.2. And both of those are exactly the same. Any place that I wanted to pick on my perpendicular bisector is going to make isosceles triangles if I connect them. They're going to be the same distance. They're going to be equidistant. So that's what the theorem says. Any point on the perpendicular bisector, any point that we want at all, is equidistant to the 2 endpoints. It's the same distance away from A as it is to B. Because basically you cut that segment in half, which you made 2 equal pieces already. So just connecting those is going to make two equal lines. All right, let's move to the last thing that we want to talk about here. I'll come back to it. Let me just do the HL theorem because it's on the back side. Grab your compass, and there's a segment there for you. We're going to make a perpendicular bisector, but we're not going to draw it as long as we did the last one. So here's what I want you to do with your perpendicular or with your compass. Take your compass right now, put it at one endpoint, and open it up so it's past halfway. And simply just make an arc at the very top like you did when you were making your isosceles triangle. Actually, what we want to do also is make one at the top, and then we're going to also make one at the bottom. And then you're going to do the same thing from the other side. Okay, so from the other side, you're going to make an arc there and an arc up top so that they intersect. It's kind of like the fish without the body. And that's actually what you see most of the time with perpendicular bisectors. You usually don't see the whole fish. Usually you just see the top 2 arcs and the bottom 2 arcs and where they connect. Take your protractor or your straight edge, and you're going to line up where those two meet like that, so you can see that they would connect. And then instead of drawing in the whole line, just draw the line from this dot down to the line itself. So you just want to draw that far. So we just want to draw it that far. And then connect this point where you drew it from to each side. Again, making what kind of a triangle? Isosceles, since that's what we've been talking about today. We do know that this side has to be congruent to this side, because that was our perpendicular bisector theorem. And we also know that this side at the bottom is congruent to this side at the bottom. Again, perpendicular bisector tells us that this bottom piece got bisected, and the theorem tells us that any point is the same distance from the two endpoints. So we automatically know this information, and we also know that we have right angles here. So we could actually draw in our little boxes and show that those are right angles as well. So we've got quite a bit of information there. My question to you is, are these two triangles congruent? And can we prove it with what's up there? Well, yes, they're congruent, but can we prove it? Because right now I've got an angle side side. That's a bad word, right? So you can't use that one. And actually what I technically have, since it's a right triangle, and I could put sides if I wanted to, but technically, since it's a right triangle, I can put H for hypotenuse, congruent to a hypotenuse. I'm going to get out of your way here in a second. And a leg congruent to a leg. So you could actually put hypotenuse congruent to a hypotenuse and leg congruent to a leg instead of the S's and the A's. You could actually put that, but does that still tell us that it's congruent? What proves? Right now we know SSS, SAS, ASA, and AAS. The one we don't use is a bad word. So out of those four, which one can we use to prove that those two triangles are the same? SSS. Why? I see two S's. Where's the third S? The reflexive property would give us the middle side in common, right? So the SSS allows us to prove that the HL theorem works. So the HL theorem says if a hypotenuse and a leg of a right triangle are congruent to the same in another right triangle, then the triangles are congruent. So all you really need if it's a right triangle is a hypotenuse and a leg, because you could turn those two triangles to where it looks like this, and you'd have a middle side in common, and you wouldn't need the SSS. You could just use HL. So if you've got a hypotenuse and a leg congruent to the same thing in another right triangle, then the two triangles have to be the same. So now we have 5 ways to do it. We have SSS, SAS, ASA, AAS, and now we have HL. And those are the only 5. There are no other ways to prove triangles congruent. Just those 5. That's congruency, not similarity. Similarity, we do other stuff. But congruency, those were the only ones for congruent. Alright, I'm going to stop here. This will be part 1.